You are welcome to Statistical Inference class, and today we'll be looking at estimation. So we're looking at estimation, look at point estimate and interval estimate. So before we talked about estimation, it's important for us to understand what statistical inference is all about. And this is a process by which we get hold of vital information about population through samples. So for every statistical inference, for any statistical inference to be made, it requires us working with what? With samples. Because of it's not in the real sense, in reality, it's not visible for us to gather all the elements in a population. So population is what we're talking about here, is the targeted group of interest your study might be upon. Group of students, group of workers, and so on. So it's not visible for you or for anybody to gather all the elements in this population. Hence, you will rely on sample from the population. So, and that is what statistical inference is all about. So it's all about making a generic information, or getting a generic information about the population using sample. I think that is clear. So now, what are the two types of inference that you can generate? We have two major types of inference, and this includes estimation and hypothesis testing. But in this class, we'll be looking at estimation as one way of generating statistical inference. So what do you mean by estimation by itself? The objective of estimation is to determine the value of a population parameter on the basis of what? Sample statistic. So, and how can we do this? How can we use sample data to estimate values of population parameters? Good. These are two ways, and these are the two methods we're going to look at it. We'll be looking at in this class. So and estimation is all about, statistical estimation is all about using our sample statistic. In previous class we talked about parameters and we talked about statistic, and we said what statistic is a function of what? Of your sample, whereas your parameter is a function of population. So whenever we refer to statistics, you know that we're talking about the function of a sample. So the estimation, the values you derive using the statistic, that means the function, the statistic of a sample statistics, is what gives us estimation. And this comes in two forms. One is point estimator, the second one is interval estimator. So what is point estimations? As it sounds, point, just a single value. That means the sample statistics that produce just a value, and we call that value best guess, best fit, accurate enough to represent the population. So it's just a single value. So a point estimator draws inference about a population by estimating the value of an unknown parameter using a single value or point. So it's a point estimate, it's direct. Example of it is mean of a sample. So the mean the mean will give you just a single estimate. Oh, that's x bar equals to summation of x over n. It just produce a single value. And another example is variance, sample variance. These are what produce what? Single digit or single value or single point. Good. So how does this work? To further explain this, look at the diagram below. The diagram we have there. What you have here, you see that what out of your sampling distribution, that means for instance, let's say your mean sample distribution. Look at it. So we'll pick the best guess. So the best guess happens to be what? The red point here, to be the point estimate. And you could see that what E is the, before we have two normal curve. The bigger one, the upper one, represent the population, which is the parameter. You could see that what we have a parameter. That's a function of the population. While the sample, which we used, or you were using to estimate the parameter, is below. It's just a small part of the sample of the population, and whatever should be the value of your estimate here, that's point estimate, definitely it will represent sorry about that, the parameter that is unknown in your population. So that's what we call, so the typical picture of how point estimate looks like. So we've treated this in our previous class. Also, this is an example of an exercise on point estimations. We'll look at the length of an individual machined part coming off a production line and set to follow a normal distribution, and the mean is about 30 centimeter. So the mean here represents the what? The population mean, you could see. So since we said it's 30, so that's population mean, and with a standard deviation of what? Of 0.1. And the inspector just took a sample of 4. So now we have a sample size of 4 out of the whole of this part, and found out that what the mean of this sample is 29.8 something, 29.87 centimeter. So the question is that what is the probability of getting a sample mean that is below or lower if the process is still producing at that mean of what? 30. You could see. So what would be the answer? We've estimated this in our previous class, so you can see our previous class on sample and sampling distribution. You will see. So our second one is point estimation and interval estimation. And interval estimation. The interval estimation we're talking about here is just an opposite of what? Of point estimate, in the sense that here we don't have a best guess, or we don't have a single value. Rather, we have a range of values or range of estimation where your sample statistic would fall in. So it's quite opposite, So it makes it of an interval, and that's what called refers to as interval estimate. So an interval of numbers around the point estimate. So your mean can be said to be what? To be between so point and so point. And for every interval estimate, there is confidence interval, or the confidence level rather. So the confidence level, when the confidence level is implied, it becomes confidence interval. And this, we're going to look at this detail of this example in this class. So as I said, interval estimate, unlike point estimate, is what? It makes of what? There are intervals of values from point A to point B, not unlike point estimate that I'll just pick only one point. So before we go in details, what are the characteristics of good estimator? So every estimate, any estimate that is good, must possess these important properties or characteristics. One is unbiasedness. Unbiasedness means that what? An expected value of that statistics must be equal to the parameter of that population. So that's one bit. So when you take, for instance, if you have a mean, or from the sample mean of what, you get a sample mean of 30, you understand? So that 30, the expectation of that 30 must be the same with your population mean. And we've shown that in our previous class, where we take the expression of x bar and we open the bracket and we expand and give us what? The population mean. So this is what we refer to as unbiasedness. Then we have consistency. Consistency simply means that an unbiased estimator is said to be consistent. So if you have an unbiased estimator, now it's said to be consistent if the difference between the estimator and the parameter grows smaller as the sample size increases. You said if the difference between your estimator and your parameter grows smaller, sample size increases, what? To be consistencies, because we said the more you increase your sample size, the more it tends to be what? Normal, and hence the gap between your estimator and your parameter will be reduced to minimum. So that's mean by what? Consistency. So the third one is what? Is relative efficient. So here, what this is implies that if you have two estimators that are unbiased, or estimator A, estimator B, that if they are unbiased, the one with the minimum variance is said to be what? Relatively efficient. So here you have two unbiased estimator, A and B, and they are producing they are meant to produce or to give a particular to represent a particular statistics or a particular parameter. So these two, the variance is then compared. Why are you comparing? You are comparing to in order to pick, to know which one has smaller variance, and the one with the smaller variance is said to be what? More efficient than the second. So these are the things you have to have at the back of your mind. So let's look at how we can, some examples of confidence interval estimation. So let's look at estimating confidence interval of population mean when the population variance is unknown. So how do we do this? How is an interval estimator produced from a sample distribution? One, a sample of size n is drawn from the population and its means is being calculated. So the first thing is that what? From the population you draw out a sample size, and desired sample size of n, depending on your target. And what do? You calculate the mean, and then by the central limit theorem is normally distributed. So thus, what do? We apply our central limit theorem to it, and this is the next slide explains it better. So this is what we implies. Okay, how do you estimate it? Before we said draw out your sample size and calculate the mean of your sample size, and what? Standardize it. So this standardize, it simply means application of what? Central limit theorem. And when you do this, and what you are doing here is that what? For a particular value, you could see that we have a band. There's a boundary, there's lower bound, and there's what? Upper bound. And how do you depict that, the lower and upper bound? Yes, they are all estimating mean. You get expressing as estimating mean, population mean. Want to estimate population mean. So know that what? If you want to estimate population mean, what you have to do is what? Make mu the subject of the formula, right? Good. That's the essence. You understand? We want to make mu the subject of the formula, and that is our goal. If you make mu the subject of the formula, what you're supposed to have what? This cross multiplied to here. So you have z times this, then equals to what? X bar minus mu. Remember, what do you want to do? We want to make mu subject of the formula, or rather, let's first make x bar subject of the formula. So if this moves here, it turns positive, right? That means it turns positive. So therefore we have this function to deal with. And if for a lower bound, what do? We use negative. So since your mean is static, it's a population mean, remember, is a single value. So for you to have a lower value of it, what do you need? You need to deduct this z product of sigma over square root of n. And for you to get the upper value of it, what do? You add this and equal to what? The confidence level you intend to use. So this alpha could represent 5%, could represent 1%, could represent 10%, just as the case may be. To that. So if that is being done, the next thing is that what? You make what we are looking for is your population mean, remember. So we have to make the subject of the formula. So you make the subject of the formula, then this stands. So you can then now estimate. Your estimation here will give us what? A particular value, and here will give us a particular value. Hence, based on this confidence interval that will be applied in your z there, then we can now say what? The parameter, the population mean, is between so value to so value. Hope that is clear. So that's what I just explained. So here you have what? The lower bound, and you have the what? Now you have the upper bound. So how does it look like on the normal curve? So this is how it looks like. So as I said, the lower confidence limit, which I referred to as lower bound earlier, is this, and you could see to give this. So if we're being given this, so it's the confidence level or that you are estimating falls within here. You understand? And that is the what's it called? In percentage. So if it's 5%, so that means this is a 95% confidence level you have. And if it's 1%, that means that's 99% confidence level. So confidence level, the alpha can vary for any values. So that is the confidence level we're talking about here. So if you're using 90 for your z, alpha over 2 will be this. Use 95, this will be your z. This will be your z, this will be your z, as the case may be. So let's consider an example. We want to estimate the mean value of a distribution resulting from a throw of a fair die. So, and the standard deviation of that process is what? Is 1.71, and we have to use 90% confidence level. And if this is being repeated 100 times, so this our end there is what? 100. So when you apply the earlier formula stated in our previous slide, what do you have? So this it takes already taking a lower and upper bound or confidence limit already. So when you introduce this, since you are dealing with 90%, so the z of this 90% will produce 1.645, and when you introduce your standard mean, your standard deviation and the sample size, you have 0.28. So this is what you could say that the sample mean is what is less minus 2.8 as 0.28 for the lower bound, and for the upper bound will be what? The sample mean plus 2.28. So whatsoever you have as your sample mean, you have this. So to give you a value. So how does it look like when we're dealing? Let's consider 95%. 95% confidence interval. So what do you still the same thing? So what varies is at what changes here is your Z. So your Z will now be 1.96 instead of what? The previous Z in the previous slide. So the confidence intervals influences the confidence, your result. So before it was what? 0.28, now is what? 0.34. So you can try it for others. So you can try. Let's look at another example. Look at how this is being done. And we have standard deviation of 75, and we want to look at confidence level of 95. So we assume arbitrarily, let's pick that the mean of that process is 370.16. So what do? We introduce that, substitute the necessary value there. At 9.5, you have what? You have this. You have this to be. This will give you 1.96 because it's 95. You understand? And when you do the mathematics here, and this will result to the lower band of 340.76 and upper band of what? 399.56. So we can say that what the sample mean is what? Is between, or the population mean for that process is between 340.776 to 3.99.56. I hope that is clear. So please do well to drop your question. If there's any questions in our comment, we will gladly attend to them. Thank you, and that's the end of the class.